Yeah, think about this. You're trying to clock a sprinter, right? But imagine every time the gun fires, the track just dissolves into fog. And the finish line, it keeps jumping around randomly. How on earth do you measure time if you can't really define now or then? See, in our everyday world, with wristwatches, kitchen timers, time seems simple. You just count seconds between 2 points, Easy. But down at the quantum scale, where electrons are just this buzz, this blur, that whole idea of counting seconds, of starting a clock at zero, well, it's basically useless. So today we're doing a deep dive into this really fascinating study from 2022. Researchers from Uppsala University in Sweden. They're proposing a totally new way, a non-sequential way to measure time, really, really short time, femtoseconds, and they do it by looking at the shape of the quantum fog itself. Our mission here is to try and understand this breakthrough and figure out why it might mean we just don't need that fixed 0 point anymore when we're timing the universe's fastest stuff.
Yeah, this is a perfect example, really, of physicists needing to get, intensely creative when the old classical rules just stop working. The fundamental challenge here, the thing they're solving, is that at the quantum scale, just trying to observe or measure now actually messes with the system itself. So trying to use a normal stopwatch, it just won't work. Because that starting line, the then, you can't always predict it. And crucially, the present moment, the now, it often just blurs into this haze.
That blurring, that haze, that's the real problem, isn't it?
Yeah.
I mean, the uncertainty principle tells us we can't know a particle's exact position and momentum at the same time. So how could we possibly nail down its duration? It really sounds like trying to build a clock out of smoke.
Well, yes, in a way. But it's a predictable kind of smoke, if you like. To even start this, the researchers needed a particle they could work with. Something that, holds on to its quantum nature, but is still big enough, relatively speaking, to see subtle changes over time.
Okay, right. Let's unpack that. And the key component here is something called a Rydberg atom. I love the analogy they used in the source. They called them the overinflated balloons of the particle kingdom.
Yeah, it's a great description, actually, and pretty accurate. Technically speaking, a Rydberg atom is one where you've nudged the electrons into really high energy states. This makes them orbit super far from the nucleus, like thousands of times further than normal. That huge distance gives them that overinflated quality. And we basically puff them up, as you said, by hitting them with very specifically tuned lasers.
Right, and making these Rydberg states, this isn't just some lab trick, is it? It's actually a big area of research already.
Yeah.
For quantum computing and things like that.
Exactly right. Inducing these states is a really valuable tool for engineers, particularly when they're thinking about designing new kinds of components for quantum computers. And besides that, we already use lasers for measuring really fast things. There's a technique called pump probe.
Okay, tell us a bit more about pump probe, because understanding how that works and its limits really makes this new idea stand out, I think.
Sure. So in pump probe, you basically use one very short, intense laser pulse, that's the pump, to excite whatever system you're looking at. Then, a tiny fraction of a second later, you hit it with a second short pulse of the probe, which takes a kind of snapshot of the change that happened. By carefully changing the time delay between that pump and the probe, you can sort of stitch together a movie, a timeline of what's happening, like watching electrons move in ultra-fast electronics.
Okay. So those methods do measure time, but they absolutely depend on counting sequentially, right? And having that fixed starting point.
Yeah.
You have to know when time equals 0, when the pump hits. Then you physically measure the delay until the probe pulse.
Precisely. You're relying on external things, macroscopic devices like the equipment that controls the probe pulse delay, to define the time. And that dependence, that's a major hurdle, especially when you remember how sensitive these quantum systems are to being disturbed. If that moment of excitation, your 0 point, is already fuzzy because of quantum uncertainty, well, then your measurement of the time passed is going to be fuzzy too. And that's exactly why this Uppsala work is so exciting. They basically get rid of the external clock entirely.
Okay, here's where it gets really, really mind-bending for me. Let's talk about what these electrons do once they're in that Rydberg state. You said it's chaotic. The source says they're not like beads sliding about on a tiny abacus, like, nice and predictable.
No, definitely not. Their behavior is way more complex. It's fundamentally probabilistic. The source description is actually pretty good. It's like an evening at the roulette table where every roll and jump of the ball is squeezed into a single game of chance. For any single electron, its position at any moment, pure probability.
Right, I get the roulette wheel analogy. But here's the jump I think might lose people. How do you get a reliable, precise timestamp, like exactly 4 nanoseconds, out of pure chance? If the electron's position is unpredictable, how is the time predictable?
Ah, that's the clever part. It's about using the wave nature of the particle. So while one electron's position is unpredictable, the mathematical rules governing its probability field, what physicists call the Rydberg wave packet, that is highly predictable. Think of it like this. The single marble on the roulette wheel is chaos, yes, but the laws of probability that describe where that marble might land, those are solid, rock solid.
Okay, so we're shifting focus. We're not looking at the unpredictable particle itself, but at the predictable probability cloud around it.
Exactly. When you excite an atom into a Rydberg state, you're actually creating a mix, a superposition of many of these energy states. Think of it as multiple wave packets rippling out at the same time in the atom, and when you have enough of these wave packets rippling around, they start to overlap and interact. That interaction is called quantum interference.
Ah, like dropping two pebbles in a pond. But, way more complicated. The pattern where the ripples cross over isn't random. It's a direct result of the physics and how long it's been since the pebbles dropped.
Precisely that. And those unique interference patterns, they become the physical, measurable fingerprints of time. Because the way these Rydberg wave packets evolve is dictated by fixed quantum laws. The interference pattern you get after, say, 1 nanosecond looks totally different from the pattern after 2 nanoseconds. The pattern itself is the clock. So the physicists, they set out to test if these fingerprints were consistent. Were they reliable enough to use as a quantum timestamp?
That's incredible. So you're literally just looking at this complex, shimmering pattern, and that pattern instantly tells you how much time has passed. It's like scanning a barcode instead of running a stopwatch.
Exactly. And it turns out that barcode is incredibly stable and reliable. The research involved measurements on laser-excited helium atoms. Helium's good because it's simple enough to calculate these quantum states accurately. They observed the interference patterns and checked them against their theoretical predictions. That validation was absolutely key to proving these patterns really are universal markers for duration.
And huge benefit is right there, isn't it? You don't need that external start signal anymore.
That is the absolute key takeaway. Marta Berholtz, the physicist who led the Uppsala team, she put it really well. She said, if you're using a normal counter, you have to define zero. You start counting at some point. But the benefit of this new approach is you just don't need that external setup. No 0 point needed.
You just look at the pattern, and boom, you know the time.
You just look at the interference structure, and you know the duration since the atom was excited. In her words, the benefit of this is that you don't have to start the clock. You just look at the interference structure and say, okay, it's been 4 nanoseconds. It completely bypasses that fuzziness around the start time because the measurement is actually built into how the system structure evolves over time.
Wow. Okay, so connecting this back to the big picture, the major implication here is that none of these time-telling patterns need a then and now. No start and stop point. It's purely measuring the evolution itself.
That's exactly it. It completely reframes how we measure time in the quantum world. We're moving from sequential counting to pattern recognition. Think of it like this. Instead of timing an unknown runner with your stopwatch, you're comparing the structure of their progress against, a known, very detailed map of how a quantum system should evolve. The map itself tells you how far along you are in time.
And the precision is just staggering. This isn't just a theory. They got real data from this. The research showed they could timestamp events lasting just 1.7 trillionths of a second. A trillionth of a second. It's hard to even wrap your head around that.
Yeah, that time scale, or rather that shortness of duration, is absolutely essential if you want to observe really fundamental processes. Things like chemical reactions, energy transfer between molecules. So this guidebook of evolving Rydberg wave packets, these predictable patterns, they could be really useful right away, especially when combined with existing tools like that pump probe spectroscopy we talked about.
Right, because with pump probe now, if your starting pump signal is weak or noisy because of quantum effects, your whole measurement gets messy.
Yeah.
But with this new method, you almost don't care about the quality of the start signal.
Pretty much. It gives you this robust internal timer for measuring things happening on these tiny scales where maybe traditional timing is just too clunky, or where that quantum uncertainty makes defining a sharp start and stop just impossible. This makes it a potentially incredibly powerful tool for watching, say, exactly how quickly electrons jump around during a chemical reaction or how energy moves through a new material.
And looking forward, the research which was published in Physical Review Research, it mentions there's lots of room to expand this. The team could use different atoms instead of helium, right? Or maybe different kinds of laser pulses, different energies.
Exactly. Doing that would broaden the guidebook of timestamps, as they call it. It would create more patterns, more reference points, making the technique useful for a wider range of conditions and experiments.
So it's like they're building a universal internal timing system for the quantum realm.
You could say that. It almost democratizes ultra-fast timing, in a sense. You might not need hugely expensive, complex external timing gear anymore. You're just using the fundamental physics inside the atom itself as your clock, which, brings up a really interesting question for you, the listener, to maybe mull over. If time at these tiny scales can be measured just by looking at structure, at patterns, rather than by counting seconds, does that change how we think about causality? About cause and effect? If there's no absolute zero, does cause always have to come before effect in that simple linear way we usually imagine it? Something to think about.
That is a fantastic thought to end on. The idea that cause and effect might just be a pattern, not a sequence. Wow. Well, if you enjoy this deep dive into how the shape of quantum fog can tell time, please do let us know. We really love digging into the topics you suggest and trying to make this complex science a bit more accessible. So please like and subscribe. Maybe click on our affiliate links for some great books on quantum physics. We'll drop those below. You can even blog about your thoughts on this episode. And definitely leave comments suggesting new topics for us to explore. Your engagement honestly does help us keep these deep dives going. Until next time, stay curious and be sure to come back for our next deep dive.